Hi, I'm Ryan Baker, and this is Big Day in Education. You probably knew that by this point in the course, but still. Today we're going to continue our grand tour of knowledge inference methods with item response theory.
Item response theory is a classic approach for assessment used for decades in tests and some online learning environments. In its classical form, it's got some key limitations that make it less than useful for assessment on most online learning, but variants like ELO and CDM address some of those limitations. We'll be talking about all this today.
The key goal of IRT is different than the key goal of BKT or PFA. It's to measure how much of some latent trait or general domain a person has. So instead of saying, can Bob do 2 plus 5, it says, how smart is Bob? Instead of saying, does Bob know this specific skill about snorkeling, it says, how much does Bob know about snorkeling in general? You may wonder about my snorkeling example. You should probably check out Snorkel Tutor, which is available in your snorkeling app store. A typical use of IRT is to assess a student's current knowledge of a general topic X, general domain, based on a sequence of items that are dichotomously scored. In other words, a student can get a score of 0 or 1 on each item.
Now, IRT makes some key assumptions. The first, and kind of the most controversial, is that there's only one latent trait or skill being measured per set of items. Now, this assumption is relaxed in the extension cognitive diagnosis models, but in core IRT, there's just one skill, one general ability. How smart are you in math? Another key assumption that's particularly questionable for online learning is that no learning is occurring in between items. In other words, you have a testing situation with no help or feedback. Now, in most systems where the student's actually getting better, we don't necessarily want to make this assumption.
Another assumption, each student has an ability called theta, and each item has a difficulty, B, and discriminability, A. We'll talk about what discriminability means in a second. From these parameters, we can compute the probability, P of theta, that the learner is going to get the current item correct. Now, the assumption is, again, that all items tap the same latent construct. Everything involves math, but they have different difficulties. And this is a very different assumption than seen in PFA or BKT.
The simplest IRT model, and a very popular one, is the Roche model, also sometimes called the 1PL model. Now, Roche and 1PL are mathematically the same model with a different coefficient, but there's some different practices surrounding the math that some people take very seriously and are outside the scope of this course. In fact, there's an entire special interest group of AERA, the American Educational Research Association, devoted solely to the Roche model and modeling related to Roche. But we're going to treat these the same for the purposes of this discussion.
It's got no discriminability parameters, so we're going to hold off on talking about that for another minute. But it does have two sets of parameters, a set of parameters for student ability and a set of parameters for item difficulty. Each learner's got ability theta, each item has difficulty B, and you can compute the probability that student will get something right by a function involving an exponential function with theta minus B. So we take the ability, we subtract the difficulty, they're on the same scale. In IRT, we can understand an item's difficulty by looking at, for that item, the relationship between student skill and performance. As you can see on this graph, the x-axis is the theta, student ability, and the y-axis is correctness. And when theta equals 0 for this graph, probability of correctness equals 0.5. This actually has to mean that B is equal to 0, because for P of correct to be 0.5, theta and B have to be exactly balanced. So now let's look at the item characteristic curve. This is a visualization that shows the relationship between student skill and performance. This graph represents B equals 0. When theta equals B, knowledge equals difficulty, performance is 50%. So in other words, if you look across the x-axis and at the thetas, theta 0 is 50%, so this has to be B equals 0 as well. And the y-axis has the probability of correctness. Now let's look at three students. A green student who really knows their stuff, theta of 3, probability of getting it right 95%. A student who doesn't really know their stuff, theta of 0, probability of getting it right 50%. And a student who really doesn't know their stuff, theta of negative 3, probability of correctness of 5%. Now, if we change the difficulty parameter, we get different lines. If you look at the green line, B equals negative 2, that's an easy item. In this case, the student with theta of 3 doesn't improve much, but boy, the student with theta of 0 goes up from 50% to 88%. And the student with theta of negative 3 still goes up a good bit, from like 5% to almost 30%. The orange line is B equals 2. That's a hard item. So in other words, now the really good student, even the really good student, who's kind of theta of 3, has only a 70% chance of getting it right. The student with a theta of 0, the average student, is barely above 10% chance of getting it right. And the student whose theta of negative 3, just no hope. Now you notice the good student finds the easy and medium items almost equally difficult. Like if you look over that top right corner of the graph, you can see that way up at the top, if the item is easy or medium, it doesn't really matter if the student's really good. And similarly, if you look down at the bottom, the weak student finds the medium and hard items almost equally hard. So IRT is most informational, kind of close to the middle for items and close to the middle for students. Now you'll note that when B equals theta, performance is 50%. And so this happens all through the spectrum. If you got a really easy item and a really weak student, they're going to get performance of 50%. If you got a really strong student and a really hard item, you'll get performance of 50%. This model accounts for the fact that difficulty of items and skill of students can be in balance. Another simple IRT model that's pretty popular is the 2PL model. In this one, there's a discriminability parameter A added. Now, if we look at the Roche, we can see that the 2PL model is exactly like the Roche, except that -1 up in the Roche becomes a -A. So if you have a 2PL model where A equals 1, it's the Roche model. Now if we look at different values of A, we can see that the green line has A equals 2, and that gives it higher discriminability. It's kind of making a faster transition as students get better between being really hard and really easy. The blue line, A equals 0.5, has lower discriminability. It makes a much slower transition as students get better between correctness and incorrectness. Generally, you want items with relatively high discriminability, although in some cases being too high for discriminability isn't very useful because it only distinguishes a very small set of the range. So if we look at extremely high and extremely low discriminability, if you take a look at red, the line where A equals 0, there's no discriminability. People do equally well no matter what it is. I guess that would be a coin flip. How likely are you to guess a coin flip? And as A approaches infinity, you get something looking more and more like the green line, where there's just this very small range between getting it wrong and getting it right. So even though this is very discriminable, it actually may not be useful because it's only going to tell you the difference between, in this case, students with a theta of about -0.1 and students with a theta of +0.1. Anything below or above that range is just going to be completely certain to get it right or wrong. Is that clear? And finally, there's model degeneracy, which can't happen in Roche but can happen in 2PL when you get A, discriminability below 0. In this case, the model actually tells you that the smarter you are, the more likely you are to get things wrong, and the less strong you are as a student, the more likely you are to get things right. This is kind of even more of a weirdness than it is in BKT. Finally, not finally, because there's tons of stuff in IRT, it's a huge area, but finally for today, there's the 3PL model, which is a more complex model, which adds a guessing parameter, C. And this might look kind of familiar if you remember BKT. The probability you get things right is the probability you guess it, plus the probability you didn't guess it, times the probability you knew it. So either you guess and you just get it right, or you don't guess and then you get it right based on knowledge. Now how do you fit an IRT model? You can do this with expectation maximization, as we discussed in the previous lecture. You estimate knowledge and difficulty together. And then once you've done this, given an item difficulty estimate, you can take a new student and assess their knowledge in real time. So IRT is used quite a bit in assessment, and on the online world you see it in computer adaptive testing. Testing that tries to infer what a student knows and tries to give items the right level of difficulty and discriminability to better pinpoint what the student knows. It's not used quite so often in online learning, where student knowledge is changing as we assess it, and IRT doesn't have any provision for that. For those situations, BKT and PFA are more popular.
It's worth briefly mentioning one extension to IRT, which is ELO. ELO has been around for a long time. It was used to rank chess players. It's a variant of a Roche model that can be used in a running system, which is a big difference than classical IRT, which makes estimates kind of post hoc. It continually estimates both item difficulty and the student ability, updating both every time a student encounters an item. ELO does this based on two very simple formulas, where it changes the student parameter and it changes the item parameter every time it encounters a new experience, taking the difference between the student's actual response and the predicted response and weighting that by some factor k, a parameter for how strongly the model should consider new information when updating the new estimates of ability and item difficulty. And next up, advanced BKT. Thank you very much.